Hello, my name is Maximilian Hünemörder, and I'm from the chair for Information Systems and Data Mining from the Christian-Albrechts-Universität zu Kiel, and I would like to introduce to you our paper Towards a Learned Index Structure for Approximate Nearest Neighbor Search Query Processing. So the purpose of this paper was to have a first small foray into the concept of applying a learned index structure to approximate nearest neighbor search query processing. And nearest neighbor queries are one of the most important queries for multiple dimensional or spatial data in data mining in general, and also have risen with popularity in the last years. It's very recently we have image retrieval, like finding very close, almost duplicate images in a large database of images. We want to have we need nearest neighbor queries for recommender systems, like finding similar movies to a certain movie, similar users to a certain user, and general in data mining. And this is very important, as you might know. And one extension of nearest neighbor query processing in these recent applications, for example, image retrieval, is that we don't actually need like the exact nearest neighbor, but we can find an approximate nearest neighbor instead. For example, we would have a lot of images from the same object, so it doesn't not matter as much if we get the exact closest image or one of the others around it. And we can use this approximation to speed up our nearest neighbor queries, but of course we trade this with the accuracy, the precision, the recall of this nearest neighbor query. Methods that are doing this have existed for a long time. We have traditional hierarchical index methods that also work for exact queries that can be changed to work with approximate nearest neighbor queries. We have very important the hashing methods, famously locality sensitive hashing for more bigger data that are hash functions that are applied to data points, and the buckets are these functions are designed so that the points that are thrown into the same bucket have some kind of similarity, and so if we get a query object, we can apply the same hash function or functions of family, and if we find a bucket where there should be similar objects in there, but we still need to find them in this bucket, the similar objects, and it's also just an approximation. And last but not least, we have vector quantization and compression methods, which also are quite similar to what we are doing, and we will see that now. What we want to do is apply the concept of learned index structures to this approximate nearest neighbor search query. The concept of learned index structure is something rather recent. It was introduced in a paper of the case for learned index structure, or it was at least not introduced, but made popular in the paper, The Case for Learned Index Structures, where a team where the authors introduced the concept of traditional one-dimensional database indices and combined them or saw them as a learning task, redefined them as a learning task, and applied different predictive models to imitate or replace these traditional index methods, for example, Bloom filters or general search trees. This was then or can be applied to multidimensional, which they don't do in this paper, but has been done from here on out. And we are especially interested in nearest neighbor queries or approximate nearest neighbor queries. I would like to emphasize one work, which is the learned metric index from Antol and Slaninakova, which actually one of those papers what we have down here was sent also to SISAP this year. So I would ask you to head over to that video after this one and check out their work as well, because they have similar results as we, and it's very cool to share this. Let's go to our method then. Our method is fairly simple. We have our data on the left here in the blue, and we want to partition it with some kind of partitioning algorithm into different buckets or pages, and then we want to train a classifier to learn the distribution of these now labeled partitions. And then if we get a query point, we don't have to use any partitioning algorithm or run it for the same index, but we can just use this classifier instead to tell us which is the most probable page where this query object and hopefully its neighbors are located, and then we can look into this page and only have to look for the nearest neighbors in this page and not in the whole data set. More formally, we have a data set D that is distributed over a set of P pages, which are of course dependent on the capacity C of the data pages. So if we have a huge load of points, and small pages, we of course have to have more partitions. The points are then assigned to a cluster or a partition by this partitioning or clustering algorithm, and then they can be mapped to the page. So the page and the cluster are in essence the same. And then we can predict the page for the query object Q with our function M. And this page we can now load into the main memory, and the nearest neighbor of Q can then be found and determined from all the objects stored on this page. And we get an approximate result because it might be that the nearest neighbor, the closest neighbor, is on the other side of the decision boundary if this partitioning was in a place where we have a very high density, and we will see that later in our results. So what did we do? What did we actually do? We ran some experiments. We tried out different partitioning algorithms, especially k-means, traditional clustering algorithm, and the leaves of a KD tree. So we ran we built a KD tree, and we only took the leaves as our pages. And we then applied different classifiers to predict our query points. We first went with the most simple one, which is basically the k-means classifier, our base model, which just means that we classify each point as the same as the closest centroid. In k-means, this is very easy because we have the centroids from k-means. In KD tree, we have to afterwards calculate the centroid for the leaf and then use that as a classifier. We also used naive Bayes with Gaussian basis. We used decision tree and random forest. We used linear and radial basis function support vector machines. And last but not least, multi-layer perceptron from sklearn, which was just a very simple multi-layer perceptron in line with the SVM in a way. We did not, since this is only a first foray, a preliminary work, we only put importance on trying looking at the applicability in general. So we did not yet perform a full hyperparameter optimization for these models. We just used reasonable hyperparameters. The dataset that we used were first some synthetic datasets. We created 20-dimensional datasets, both clustered and non-clustered. We created multiple of these with different random seeds and ran them all. Later, in the validation, we always use the mean over these different datasets. And we also tried it out on the classical image toy dataset MNIST, but since we cannot directly run on the MNIST itself, it's very high dimensional for k-means and things. It works, but it's better if we use some kind of dimensional reduction, which we in this case did with a very simple fully connected autoencoder, and then we ran the whole nearest neighbor on only the representation, not the original images. How did we evaluate this? We used 3 different evaluation methods. Mainly validation accuracy, which just means we wanted to see how well does the classifier work with the partitioning. So we did a very simple training validation split. We split up one part of the training data. We trained we applied the partitioning algorithm to the training data, then trained the classifier on this partitioning with the pseudo labels from the partitioning algorithm, and then we tried it out on our validation set, which we held back, and we got the just normal validation accuracy. For testing, we held back, we generated another lot of query points that were previously not seen from the same data process, which is our set of query points Q. And then we looked at the differences between the brute force nearest neighbor and our nearest neighbor from this page that we predicted, and took the difference, and if it's 0, so if it's an exact match, we have a 1. If it's not exact match, it's a 0, and then we take the mean of this, we sum up these 1s and 0s, and we take the mean of it over our query point Q, and that is some semblance of accuracy. So this is our test accuracy, and we also supply the actual relative error towards our dataset in our report code base on GitHub. So let's actually look at the results. So first we start with the clustered data sets. You can see down here the number of partition. We always kept the page size constant. So the page size was 10,000 samples, and the partitions then the more partitions we have, that also means that this means that we had more points. For example, with 30 partitions, we have 30,000 points. With 50 partitions, we have 50,000 points. We looked at those, and we got the test accuracy from this and the validation accuracy. First, let's look at the validation accuracy. It's no surprise that the base model has perfect validation accuracy for the whole way through, since it is basically designed to be the same as k-means. And some other algorithms are very close as well, which translates very well to the performance on the test accuracy. The test accuracy is going down the more points we throw in, and also the more partitions we gain from that, since it gets harder to classify with more partitions, and the clustering there were always 20 clusters, so if you take 50 partitions from 20 clusters, it gets harder to split this, and we can see, since it goes down, we have the base model, which performs best, but also the naive base and the RBF SVM, since they both have the same, can easily decide the same in the same structures as k-means itself. We can compare this with the KD tree results on the same data sets, where we see that here the decision tree has the perfect validation strategy, since the decision tree basically can be built the same as a KD tree, so it learns the same structure, and then it also has the best and a very similar performance on this data set. On the uniform data sets, the performance goes worse for both types. This makes sense, since if we have a uniform data set, as we saw earlier, and we kind of randomly partition it and have decision boundaries, these decision boundaries can easily split groups of nearest neighbors. So if we have a query point that's very close to a decision boundary, which gets more probable the more partitions we have, our approximation gets worse. But we still get very good nearest neighbors, which we can see from the actual relative error, since the relative error stays very low for both k-means and KD tree on both data sets. So we always get a good approximation of a nearest neighbor. The same we saw in the MNIST datasets, where we also got a very good approximation, especially with k-means, since the autoencoder representation of MNIST, as is shown in many deep learning, deep clustering works, is very close to, or is fits very well with the k-means algorithm. We get very well results from here, while the KD tree does not work as well on MNIST. Now, what can we do with this? What does it mean? So the first thing we learned is that learned index structures are very interesting and should be very useful for nearest neighbor or approximative nearest neighbor search. And we learned that the better we can estimate a data set, our partitioning algorithm, the better it estimates the densities of the data sets, and the better our data set can be split, the better our approximation gets, as the decision boundaries get better of the classifier. And so I think that this will get more attention in the coming years, and even now, since we get some billion-sized data workshops for approximate neighbor search, and in these I think that learned indices will play a role. So I'm looking forward to seeing what will happen the next time, and I'm looking forward to seeing you at SISAP and maybe discussing this further. Thank you, and goodbye.